Welcome to This Explainer. Today, we're doing something really cool. We're taking 2 massive years of incredibly dense, cutting-edge academic proceedings and translating them into a clear, accessible, thematic tour just for you. Our focus? We're going to explore the fundamentals of a fascinating, rapidly exploding field called probabilistic numerics. So think about this central question for a second. What actually happens when standard math meets uncertainty? You know, we traditionally view computers as these perfect, rigid calculating machines, right? You feed them a problem and they spit out an exact answer. But what happens when they just don't have all the facts? How do they handle the messy, totally unpredictable unknowns of the real world? Okay, let's dive into this. Traditional numerics is exact, for sure, but it's incredibly rigid. When it hits missing data or incomplete information, it basically stalls out, or it forces us to make blind assumptions. Probabilistic numerics, on the other hand, acts like a massive operating system upgrade. It actively embraces that uncertainty in estimation, giving our computers a highly flexible, intelligent way to crunch the numbers when the real world gets complicated. Here is our roadmap for today. We'll start by looking at the probabilistic numerics community, explore how they're upgrading traditional math, dive into real-world physics applications, check out machine learning and scaling, and then wrap up with the future of computation. All right, part 1. The probabilistic numerics community. To really grasp this field, you have to look at how fast the community behind it came together. Back in September 2025, the first international conference on probabilistic numerics happened at Eurocom in Sophia Antipolis, France. That gave us Volume 271 of the Proceedings of Machine Learning Research. Then, literally exactly 1 year later, in September 2026, the community met up again at LUT University in Finland for the second conference, which produced Volume 341. These back-to-back international events firmly cemented this whole thing as a major scientific movement. Now, the central engine driving almost every paper in these proceedings is Bayesian inference. Basically, by continuously updating hypotheses as new evidence rolls in, it gives our computers a profoundly better way to guess, infer, and learn when they don't have all the facts up front. Moving right along to Section 2, upgrading traditional math. So, the classical mathematical mainstays we all know are getting a serious probabilistic upgrade. We're talking about ODE solvers, linear systems, quadrature, and finite element methods, the works. For instance, in the 2025 proceedings, Nicholas Kramer introduced adaptive probabilistic ODE solvers that, amazingly, don't even require adaptive memory. And that same year, researchers Disha Hegde and John Cocaine showcased entirely new ways of learning to solve related linear systems using this exact framework. It is literally a foundational overhaul from the ground up. And this brilliantly illustrates the point. Look at this 2026 paper titled Bayes Sum, Bayesian Quadrature in Discrete Spaces by Kang, Briol, Carvonen, and Chen. They're taking quadrature and injecting Bayesian uncertainty right into it within discrete spaces. Basically, they're solving really complex foundational math problems, not by ignoring the unknown, but by calculating it directly into the process itself. Which brings us to Section 3, Real-World Physics Applications. To breach the gap between abstract equations and physical reality, just look at these 2026 solutions. For wind turbulence under aircraft motion, a team led by Amaury Kotmas-Pernay utilized physics-informed machine learning. To tackle intense physical vibration problems, Timothy Rogers and his colleagues deployed statistical finite elements. And for modeling complex gas phase reaction kinetics, Andrew Millard's team created guided particle diffusion sampling. They are literally mapping real-world physical chaos using probabilistic models, which is just incredible. To give you a sense of the sheer breadth of all this, check out this 2026 paper, Probabilistic Numerics for Hamiltonian Dynamics by De Suster, Colmont, Van Gompel, and Lee. Hamiltonian dynamics essentially describes how physical systems evolve over time. By injecting probabilistic numerics into the mix, researchers can dynamically model the uncertainty of a system's evolution, step by step, no matter how chaotic the actual physics get. Next up, Section 4, Machine Learning and Scaling. So we know the math works, right? And we know it models reality effectively. But how do we actually scale it? Well, the answer lies in integrating these methods directly with advanced machine learning. In the 2026 proceedings, Jonathan Hummel and his team developed computation-aware Kalman filtering for neural dynamics. We also saw Tim Weiland's group focus on scaling up probabilistic PDE simulators with structured volumetric information, and Robin Young's work on amortizing Gaussian process inference with neural processes. These researchers are pushing the absolute limits to ensure these heavy probabilistic calculations can actually run efficiently, at scale, inside modern neural networks. Now, what's really interesting about this slide is this 2025 paper from Quishuo Ho and team, Online Conformal Probabilistic Numerics via Adaptive Edge Cloud Offloading. Just think about what that title implies for a second. We're not just talking about theoretical math anymore. They're literally designing ways for these massive probabilistic calculations to be split dynamically between local edge devices and the cloud. This proves the math is already moving out of the lab and directly into our real-world computing infrastructure. Finally, Section 5. The future of computation. Looking at the core methodology across dozens of these papers, a clear pattern emerges. Step 1. Accept uncertainty. Instead of forcing exactness where there literally is none, we have to embrace the unknown. Step 2. Apply Bayesian inference. We give the computer the statistical tools to continuously update its best guess based on new evidence. And Step 3. Solve complex reality. Because once we do that, we can apply this upgraded mathematical framework to everything from airplane turbulence to deep neural networks. And I want to leave you with this final, truly profound thought. In the 2025 proceedings, Frederick de Soyster, Tom Colmont, and Johnny Lai published a paper titled Solving Einstein's Equations as Bayesian Inference. Just let that sink in for a moment. They're applying probability and estimation to the very equations that define gravity and the fabric of space-time itself. It leaves us with a massive, super exciting question. If we can rewrite Einstein's math using probabilistic numerics, what part of the universe will we decode next? Thank you so much for exploring with me, and I hope this provided a clear window into an absolutely amazing field.